it is possible, and this really annoys me that sometimes the fraction marks show up and sometimes they don't, and I have no clue why. Obviously, when you see two terms on top of one another and there's no line there, it's intended to be a fraction. When I create these, I see them, and then when I post them to the web, they go away for some reason, occasionally. So it is possible to determine SHmax from breakout data. So basically, we use the Kirsch equations, or the simplified Kirsch equations at the wellbore wall, combined with some type of logging data that where we observe breakout and their width. And in fact, this WBO here is the breakout width in radians. Okay. It could also be in, if you, instead of pi there, if you had 90 degrees, then that would, you could have it in degrees as well. So this is the width of the breakout as observed from some well logging, either caliper or ultrasonic, right? So if we have the breakout width, we can also measure, and we'll talk more about this when we talk about hydraulic fracturing, but we can measure SHmin from mini frac tests, or essentially intentionally hydraulically fracturing the well and then measuring and then allowing it to leak off and allow the fracture to close. We can get an estimate of SHmin from that. So then if we have SHmin, if we have data on the breakout strength, and then we also know the unconfined compressive strength of the rock, then we can find SHmax. So SHmax is the hardest of the three principal stresses to determine in magnitude, right? Because the vertical we can estimate from the overburden stress. The SHmin we can get from some type of hydraulic fracture test, but then we have to infer SHmax from that data and other information. Okay. By the way, this also assumes a more Coulomb type failure model. So if the rock behaves in such a way that more Coulomb's not actually a good model, then it's an additional complexity. Okay. So this is just a rough estimate, but yeah. It's the simplest model that does a decent job describing rock. Again, before the break, I think in the 2 lectures, certainly to the lecture right before spring break, if you haven't watched it yet, we talk about other models. So there's like, I think the Hoek-Brown model, Drucker-Prager, there's many other types of models that do a better job of realistically capturing the effects of rock. So I think the big one we talked about before spring break was pressure dependence. So with more Coulomb, the amount of hydrostatic pressure on the rock doesn't matter. You can continue to apply hydrostatic pressure to infinity, and you'll never, when you let it go, the rock, according to the more Coulomb model, the rock will just go back, just undeformed back to where it was elastically. But we know this is not physically true, right? If I go and if I could actually apply hydrostatic pressure to a rock, or basically anything, to infinity, there's always going to be, when I let it go, there's likely to be some permanent deformation. Okay? And in rocks, there's certainly permanent deformation, and it's associated with collapsing pores. So as I squeeze the rock, I collapse the pores out of it. And then when I let it go, they don't rebound. They've actually been crushed out, so permanently. And I can do that without actually failing the rock in the sense of, like, you know, breaking the rock into 2 pieces. Like when you go and you do an unconfined compressive test, you know, you squeeze the rock and it splits into 2 pieces. Right? If you just squeeze it hydrostatically, you can permanently deform it without actually failing it. And so in order to describe that type of behavior, you need a more sophisticated model that has an end cap or pressure dependence. But if you use this model, then you can, you can build up these kind of these kind of data. So, I mean, this is just, and I'm actually having to jump around a lot because I don't really like the way that it's presented in Zobac's book. So basically what we were talking about up to 2 slides ago was in chapter 6, and now we're into chapter 7 here, where we're here using breakout data and SHmin from hydraulic fracturing to infer what SHmax is. And so this graph comes from chapter 7.